Whoops. All right, so we're going to talk about the shape. How does it look? Is it symmetrical? Is your graph symmetrical? Is it a bell-shaped curve? Is it a U-shaped curve, right? Looking at page 15, normal bell-shaped curve, U-shaped distribution, asymmetric, unimal, right? These are all examples that we could talk about when we're talking about the shape. You can talk about the number of peaks. What's a peak? Yeah, the highest point. How many modes is the highest point typically a mode? Yeah. How many peaks? Or the opposite, how many valleys, right? If it's going down. Or we could even talk about gaps. Are there any gaps in this shape? Is it symmetrical except there's a big gap? Right? Vocabulary. Don't just say it looks good. The one that everybody loved is skew. We can talk about the shape of a graph because we can describe the skew of it. What are the two types of skew? Right and left. Left skew or right skewed left. Right skew. There are other words that can describe these. Positive and negative. Right? Left skew is negative. Right skew is positive. The way that I tell myself that is like if something's right, it's a positive point on your test. It's a stretch. Skew is kind of hard to keep straight in your head because a right skew graph has too much data on the left. Right? You just got to practice and kind of slow down and think about it before you start writing. All right, I'm going to draw 3 graphs. You draw 3 graphs. These 3 graphs do not have to be exactly perfect matching mine. Okay? They need to be similar enough because we're going to talk about the shape of the graph. So if your graph is a different shape, you're going to be in trouble. But it does not have to be exactly perfect. We're going to talk about the shape of these graphs. So I'm just drawing 3 quick graphs. They do not have to be exactly perfect. They need to be very similar, though. So we can talk about the shape of these graphs. Again, focus more on, is your graph close to mine as opposed to, is it perfectly exactly as beautiful as my graphs? Are you jealous?
Yes. So jealous.
I mean, look at this guy. So we're going to talk about, we'll bring up some points. Now remember again, when you write about data, you write in complete sentences. A sentence usually consists of more than 4 words. Usually, has nouns, verbs, all that good stuff in it.
That's crazy.
I know.
That's crazy. Why would somebody say that?
You'd be shocked at what I've read. All right, so if I'm going to even this out, right? If I smoothed this out, I followed the trend of the data. Yeah? This shows me that there's a lot of data on the right side, so my left side is missing the data, correct? So what kind of graph is this? Could you talk about the picture of this? Is it symmetrical?
No.
I wouldn't even really say it has any peaks or valleys, right? It's not going up and down. It doesn't have a gap, so we need to talk about the skew of it. It is missing data on the left side, so it is skewed left. And what that means, the data is skewed left, right? My graph telling me that most of my data is on the right side. Most of my data is large, right? Because as a graph progresses, the larger numbers go this way. So most of my data is very large. However, I do have some data that is very small, right? Or less. So what happens when your data is skewed to the left, meaning there's too much data on the right side? It means that your median, the middle of your graph, is actually going to be bigger than the average, than the mean. Your median, your middle of your graph, is going to be bigger than the average. Because when you find the average, you add up all the values, right, and divide. Well, over here, finding the average of these is a pretty good idea, right? But when you throw in some really small numbers, your average is going to drop. If I gave a test, right, and I, the scores were 90%, 90%, 80%, 80%, 85, 90, 80, 80, 80, and then there was a 30%. What's going to happen to that average?
Yeah, drop in between there.
That 30 is going to pull it down. That 30 might even pull it down to a C. And did anybody actually get a C? No, everybody was A's, B's, except there was this one F that pulled it down, right? A really small number, when lots of big data occurs, a really small number will pull that average down. So the median is actually going to be greater than the mean. This graph, what can you tell me about this guy? Is it symmetrical? If I folded it in half, what would it look like?
Not symmetrical.
I mean, maybe here's the middle. It's not symmetrical. Where's the actual statistical middle of that graph? The line, there's the middle. I mean, is that even close to the looking middle? No, this is not symmetrical at all. Can you tell peaks, valleys, and gaps in a box plot? No, because you don't know individual data, right? You only know groups, chunks of data. So we have to talk about the skew. What is this one? There's not enough data on the right, right? There's too much data on the left. So this is skewed right, or positive, or right skew, or however you want to say it. And it's the opposite. Since there is a lot of low data and some really high data, right? If we were talking about, average paycheck of the people in a room, and you had a whole bunch of teachers and firefighters and everyday people, and then there was one professional basketball player, what's the average salary going to look like?
It's probably going to go higher.
A lot.
It's going to be a lot, right? Because that basketball player has a really high number, and he's going to pull everybody's data up. When really nobody makes $500,000 a year. Right? I don't make, teachers, firefighters, police officers, we're not making $500,000 a year, but that NBA player who makes $7 million a year pulled all of our data up, right? So when it's right skewed, the median, the middle salary, is actually less than the mean. Because it's pulling that data up even though it doesn't represent it. Let's talk about this frequency table, right? Or dot plot, or whatever you want to call it. Is this symmetrical? No, it's not a bell-shaped curve, right? It's non-symmetrical. All right, so could we talk about peaks, valleys, and gaps? Sure. If I kind of followed it, I could say that there are 3 peaks. What does a peak represent?
Highest point.
Which is called the
Mode.
mode. Yes, ma'am.
So, for the peak, would it be called the maximum?
No, because the maximum is the greatest value. It's the most frequent, right? It's the frequency. And that's sometimes hard to like decipher, like to get straight in your head because you're like, oh, look, it occurred 5 times. Like that's the maximum. No, it's the most frequent. It's the mode. It's the number that occurs the most, but it's not the biggest value. Now it's the value with the most in it, right? So like if this was, I don't know, what's a good one? Number of pets. So in certain cities, there are laws about the number of pets you can have, right? So probably what they did was they took a study and they found what's the most occurring number of pets people had, right? And then that was their cutoff, yes? So like if you were doing like, this person has 1 pet, this person has 2 pets, 1, 1, 2, 1, 2, right? So you're looking for the numbers that occur the most, correct? That wasn't a very good example, sorry. S stands for shape, O stands for outlier. And we've talked a little bit about outliers. You know the definition of an outlier. A definition is a data value that stands out, or values. You could have 2 outliers. The data value that are greatly is a terrible word because what is there a quantification of greatly? Like, no, it's pretty vague, right? But it greatly is different. Data values that are greatly different from the others. So part of that problem is I'm like, oh, you guys, outliers are numbers that are greatly different. My version of greatly could be completely different than Jay's version of greatly, right? Is that true? Yeah. For example, here's some data. 3, 4, I'm even going to put it in order for you because that's how nice I am. 3, 4, 5, 7, 9, 15. 3, 4, 5, 7, 9, 15. And if this was going to be, you know, oh my gosh. I'm making a toy at a toy company, and I say, okay, this toy is appropriate for ages 3, 4, 5, 7, 9, 15. I had these kids come play with it. They were all these ages. They all liked it. So I'm going to say, you know, 3 to 15. That's my age range for this toy. Do you think there's an outlier in there?
No.
Yeah.
Maybe.
Yes.
Yes, no, maybe. Like, we don't really know. I could see, like, here's a difference of 1, here's a difference of 1, here's a difference of 2, here's a difference of 2, and then you jump to 6. That's a pretty big leap, right? So, like, maybe 15 is an outlier. Maybe it's not. So we're going to use a formula to find out. Here is the formula for outliers. Ready?
No.
Yes, you are.
No, I'm not.
It's the IQR. What's that stand for?
Uniform factor range.
Nailed it. Times 1.5. 1.5 statistically represents 150%. 150%. Lily, are you there?
Yeah.
Thank you. 150%. 1.5. Then you're going to plus or minus, that means add or subtract, and I'll tell you which, to the quartiles. And I promise I will explain this to you in detail. So we need the inner quartile range. We multiply it by 1.5, 150%. And then we add it or subtract it to the quartiles. Ready? To find the inner quartile range, you have to find the quartiles, correct? To find the quartiles, you have to know the median. 6. The upper quartile is 9. The lower quartile is 4. Correct? So the IQR is 9 minus 4, which is 5. Now I'm going to take the inner quartile range, which is 5. Correct? And I'm going to multiply it by 150%, or 1.5. 5 times 1.5 is 7.5, 7.5. Here comes the plus or minus part, because it says you're going to add or subtract it to the quartiles. So you're going to take the upper quartile and add it. You're going to take the lower quartile and subtract it. Because the upper quartile, if I add it, it tells me a maximum. And if a number is bigger than that maximum, it's considered an outlier. And when I subtract it from the lower quartile, it's going to give me a new minimum. And if a number is smaller than that minimum, it is considered an outlier. So my upper quartile was 9 plus 7.5 is what? What?
16.
There you go. And my lower quartile was 4 minus 7.5 is what? Negative 3.5. If a value in your data set falls outside of that range, it is mathematically considered an outlier. So we thought maybe 15 was an outlier. Is 15 mathematically an outlier?
Yes.
Is it larger than 15.5 or 16.5 or smaller than negative 3.5?
No.
Sometimes you don't have to use this to actually know it's an outlier, right? Again, if we had a bunch of teachers in a classroom and one NBA basketball player, and we're talking about salary, could you easily pick out that there was an outlier?
Yes.
Yes. Sometimes it's common sense. But if it's one of those that you're like, oh, I don't know, you have to use the formula. 2 more. Ready? Shape outlier, SOC, stands for center. Oops, there you go. What does center mean?
The middle.
But, like most things, it's not that straightforward. There are 2 types of middles. There's the middle, which is the physical graph. And what is the other type of center? The what? The median. And we kind of talked about this already, right? We talk about it in symmetry. Symmetry has a lot to do with the middle and the median. If it's symmetrical, where's the middle? If it's symmetrical, where's the middle?
Straight down, like the center column.
Yeah, it's right in the center, right? It's the center column. If it's symmetrical, the middle is in the center. The actual physical middle is right there. Where's the median if it's symmetrical?
Same place.
I mean, right there, right? Cross out, cross out, cross out. It's right, it's literally in the middle. So if it's symmetrical, the median is the middle. Or if it's close to symmetrical, the median's probably in the middle. Like the middle of the data, it's a good statistical showing. If I showed you this graph, where's the middle of this graph? Right about here? Is that the physical middle? I'll do it in a different color. Is this about the physical middle of the graph? It's not symmetrical at all, correct? Where's the median of this graph? Where's the mathematical middle of this graph? About right here? So we'd say that the median is not the center of the physical graph. Because again, we've got those really high pieces of data on the left side and really low pieces of data on the right side. So it's pushing the median away from it. It's pushing the middle and the median further and further away. Shape, outlier, center. The last one is spread. What mathematical word do you think describes spread?
Range.
The range. It's how wide is your graph. Ladies and gentlemen, this is important information for you. I do not, when you are talking about the spread of the graph, do not just say, the range is 73. That's not a good descriptor. Because just talking about the range is not enough. I get it. Yes, you can definitely find the range. You can find the maximum minus the minimum. But so can a fourth grader. Just talking about the range is not enough. What other types of range, or how wide, what other types of range can you talk about with this box plot? You could talk about the interquartile range. You could talk in percentiles, saying that 75% of the data is greater than blank. 50% of the data falls between blank and blank. See what I'm doing there? I'm taking my analysis up a notch. I'm not just saying, oh, the data is very big. One more. Here's a histogram. Again, I get it. You could do maximum minus minimum. And you could say, oh, the range of this data is 14. That is not a good descriptor. You are right. The range is 14. What does the range mean? That's a better way to answer it. Give me more than just a number. However, are there other types of ranges that you could talk about with a histogram? What kind of ranges? Yeah, the bin width. Most of your data falls in the, let's see if this is 0 to 7. This would be 6 to 18. This would be 19 to 24, right?
0 to 7
Yeah.
is 6.
Oh, yeah. Sorry. 8 to 16. No, 8 to 15.
Oh my gosh.
6. Math is hard.
It is. It's okay, Miss
23.
Did you just do 8 to 8?
8 to 7.
She was thinking of
So
six.
0 plus 8 is 8. Plus 8 more is 6. Plus 8 more is 24. Okay, I'm there. Whew. That was tough. You could say most of the data falls in the range of 16 to 23. The two bins with the smallest frequency are blank to blank and blank to blank. Give me more than just maximum minus minimum.